Hello, I'm a math teacher in Japan. My students are from 15 years old to 18 years old. I use computer graphics a lot to teach my mathematics to my students and study mathematics for myself and for fun. In this video, I'd like to show linear transformation using my own software, Mr. Muffin. It's written by Java, so it should run over the platform. And it's free. You can download it from our website. But it can handle only linear transformation. I named it Mr. Muffin because I love muffin for my breakfast. And it sounds a little bit similar to affine transformation. There are many advantages of using computer graphics. And these are the points I'd like to show in this video. The first example, transformation by 2, 1, minus 1, 1. By this transformation, 1, 0 vector moves to 2, 1. And 0, 1 vector moves to minus 1, 1. And what is interesting of linear transformation is that you don't have to calculate at all to see the images of other points, like 2OA plus 3OB. By linearity, it moves to 2OA dash plus 3OB dash. Linearity is the most important point of linear transformation. With linearity, you don't have to calculate at all, like this one. Minus OA plus 2OB moves to minus OA dash plus 2OB. Like OA plus OB moves to OA dash plus OB dash. So you need grids to learn and teach mathematics, linear transformation, and computer can help a lot because it takes time to write grids on the blackboard. Let's do it. So let's see the transformation by Mr. Muffin. First rectangle. There is a short comment here. This is a starting point, and this is an end point. Triangle. Graph y equal minus x squared. Paint. And you can draw curves too. Choose circle. And we're going to change the color. And finish editing. So let's change the object. So there is no change, obviously, because 1, 0 vector moves to 1, 0, and 0, 1 vector moves to 0, 1. So there is no change. So we're going to change this matrix to 2, 1, minus 1, 1. The same matrix we saw in the PowerPoint. And this is the same image we saw in the PowerPoint, but there is a big difference because you can change the matrix easily and see the changes. Widening, enlargement, stretching, so what's this? 2, 1, minus 1, 2. 1, 0 vector moves to 2, 1, and 0, 1 vector moves to minus 1, 2. OA dash and OB dash are perpendicular, and the length of both vector is square root 5. So this square moves to this square. So it must be a combination of enlargement of factor square root 5 and rotation of angle theta. It should be. And you can see the result immediately. Let's draw a circle. Centered origin, the radius is 1, and transform. And then divide the matrix by the length of OA dash and OB dash, square root 5. Because we divide the matrix by the length of OA dash and OB dash, this should be a pure rotation. And this leads to, in this way, maybe you can find a matrix which rotates object around the origin by the angle of theta by yourself. So let's open the palette. This is a rotation matrix. Angle is 60 degrees, and transform. This is 90 degrees rotation, and transform. There are 5 linear transformation in the palette: enlargement, symmetric, and shear transformation. So next, let's transform an image. So let's play with her. 2001, 2002, 21 minus 1, 2. Two 1 minus 1, 1. The rotation, -90 degrees. So it was a fun. So students love this at my school. After the lesson, when I ask a question, which part of my lesson was the most interesting, and lots of students say that that is the most interesting part. So anyway, so next, so I'm going to try an animation. We're going to animate her. Rotation 1 means anti-clockwise. Yeah, so she's really rotating, and it's done by interpolation. So I put lots of 50 or 60 matrices in between 0, 1, minus 1, 0 and 1, 0, 0, 1. And you can use this rotation not only for pure rotation but also lots of other transformations. Or you can use it to the first example in the PowerPoint, 2, 1, minus 1, 1. Chapter 2, Eigenvectors and Animation. Animation is useful for rotation, which has no real eigenvectors, but it works even better for transformations, which have real eigenvectors. Next example has two eigenvectors. It works as well for transformations which have one real eigenvector, but I'm going to skip it. So comparison of two transformations which have same eigenvalues. A equal 5002. So A10 equal 510. A01 equal 201. And eigenvector is 10 and 01. And eigenvalue is 5 and 2 respectively. And B is 3124. By calculation, B11 equal 511. So 11 is an eigenvector and eigenvalue is 5. B minus 21 equals 2 minus 21. So eigenvector is minus 21 and eigenvalue is 2. So eigenvalues are same. The only difference here is the difference of base. The base of A is 1, 0 and 0, 1. The base of B is 1, 1 and minus 2, 1. And we are going to see the difference. We can see the difference by computer. We know how different it is, but we can see the difference. So A is 5002. We're going to use animation eigen. You can see the current matrix. And you can see the transformed window in a big screen. This is by A. Five times magnification along x-axis and twice as y-axis. So next, B. B is 3, 1, 2, 4. One zero vector moves to 3, 1, and 0 vector moves to 2, 4. 2, 4 and 3, 1. But it doesn't look like similar to A's transformation. So we are going to change the base. You can calculate eigenvalues and eigenvectors from here. This is eigenvectors and eigenvalues. And we are going to set the base by these vectors. I'm going to change the vector E2 from 2, minus 1 to minus 2, 1. Minus 2, 1 is also an eigenvector. And press OK. So now the base is 1, 1 and minus 2, 1. And we're going to transform this. This time, it looks similar to A's transformation. And we are going to make it bigger. Yeah, it's similar to A. You can tell that because it magnifies 5 times along vector OA and twice along vector OB. And we can compare these transformations. So let's compare. Left side is by A and the right side is by B. You can delete the orthogonal grids. Once again, so both are the magnification in one direction, vector OA 5 times. In the other, in the direction of OB, twice. So the only difference is the base vectors. And you can see this similarity even better by checking these current matrices. But if you use the base 1, 0 and 0, 1, the similarity is not clear. You have to use E1 and E2 as a base. E1 here is vector OL and E2 is vector OB, the base of this grid. The base of this grid is 1, 0 and 0, 1. So it's same if you use this or this, it's the same matrix. As you can see, there is a striking similarity between these current matrices. These matrices is a representation by E1 and E2, which means this 3, 0 means E2, E1 dash equal 3, E1 plus 0, E2. And 0, 1.5 means E2 dash equal 0, E1 plus 1.5 E2. And these 3, 0 and 0, 1.5 mean the same. So if you use the matrix this kind of matrix, you can see the striking similarity between A and B, and you can calculate this matrix by P inverse AP. Now P is 1, 1 and minus 2, 1. And if you calculate P inverse BP, 5002. Thanks for watching my videos.